we kind of left off talking about these low mass stars as they start to crush down on themselves. And they're exhausting their fuel supplies, and there's these feedback loops. They're shedding layers as they go. We talked a bit about the compositional diversity that begins to appear. The final product of all of that collapse and the shedding of all of these outer layers is this guy, a white dwarf, right? So we're basically going to examine two main roads. One is these low mass stars and what happens to them. They form these white dwarfs. And then the high mass stars, which essentially are so big that they're going to result in these violent explosions, which we call supernova. Now, there's more details to that story. There's more than one road to supernova, and there's a couple of different types of supernova that we need to talk about. But generally speaking, these are the two paths. So let's continue talking about those smaller stars that are something like around the size of our sun, maybe a little bit more, like 1.4 times. All right, so we talked about how the core was undergoing this energy crisis, and the core was hot enough to fuse fuse into carbon. And once that helium was exhausted, this pressure was no longer, the external pressure of the heat and radiation was no longer able to balance gravity. And so this core contracts and contracts. And it continues to contract until it gets so dense that it's about 1 million times as dense as water, which is very difficult to imagine. But here we are. And at this point, the material, the atoms themselves start to make a lot less sense in terms of how we think of an atom as being this very structured entity. The walls break down, the electrons are shared to a degree that they're no longer distinct from one another. And the whole thing is essentially degenerate. Now, I've mentioned this before, but a degenerate gas, a degenerate electron gas, is maybe not as exotic as it sounds, and maybe not as exotic as your textbook makes it sound, because we understand that ordinary metals are also thought to contain a degenerate electron gas as well. So this is basically a really dense kind of metal, essentially. That's one way to think about it anyways. And, if it gets to this point and there's nothing that happens to it, the idea is that this is a really stable structure, this white dwarf, and essentially it can last a really, really long time. Eventually it's going to cool down, I guess, and we'll talk about that fate. But the time scales required for it to cool down are much longer than those that most astrophysicists and cosmologists are willing to entertain. They're on the order of billions and billions of years. And so that path is generally not considered because we have this paradigm where the universe is only a few billion years old, say 14 or so at the moment. And so people don't really entertain those ideas too much, but I think they're interesting. And of course, as we are able to see further and further into the past, this timeline is expanding. I think it's going to be expanding more with better telescopes. And so maybe those are possibilities that we can entertain. There's a pretty tight relationship between mass and radius of these white dwarfs, right? And what's kind of interesting is you notice that as the mass, this is of course because it's got a lot of, it's contracting, this density is so high. And the interesting point is that on this, following from this model, at some point, the mass gets so great that the radius becomes essentially zero, which of course is preposterous, but we give that boundary a name, which is called the Chandra-Shekhar limits, which is named after the physicist who worked on these ideas a bit. And the idea is that stars that exceed this mass undergo a completely different fate, which we will get into in our black hole discussion. And I don't want to quite crack that open yet because I have a lot to say about it, but we'll play with that very soon. Needless to say, these are all stars which are sort of bound by the fact they must be below this mass limit. Now, these are pretty low mass objects, right? These are essentially about the size of our sun in terms of mass, but they're really small. So the radius here is on the order of something like the Earth, right? So it's like cramming the whole sun into the Earth, which is a very difficult picture to imagine. And that's why you get into such strange luminosities, and it's such an intense object. Okay, so let's imagine how this happens on the HR diagram, right? We talked about how these stars, like our star, can swell, right, as they undergo these feedback reactions, and the different fusion layers are pushing outwards and expanding the surface. It moves out to somewhere near where the A is on this diagram, right? This is the red giant area. So when this core collapse happens at the final stage after it's shed all its layers, once it's a white dwarf, we believe that it's moving down and starts to represent these objects that we see down at the lower left-hand corner. And this is kind of a situation where the star it cools off, it becomes less and less bright. And like I said, it's going to continue to cool and cool and cool. And of course, at this point, these stars have lost a great deal of their material. So the fact that at this point, there's something like a solar mass does not mean that they were always at a solar mass, right? They've probably lost half of their mass by this point in terms of their these ejections, which we talked about with the planetary nebula, having nothing to do with planets, but looking very much like disk-like objects. So if you start off with being a sun that's maybe 8 times the mass of ours, you probably will experience a fate similar to these white dwarfs. Now, like I said, there's a hypothetical object. Of course, we wouldn't be able to detect it, right? They call them black dwarfs because these are white dwarfs that have aged and cooled. And of course, the time necessary to cool off a white dwarf is longer than the theoretical age of everything. I do want to say something though interesting here. You know, I'm not sure how much we've talked about this. It's such a constant topic in my life, but the word universe, let's just remind ourselves what that word means in the context of astronomy and astrophysics. When you think about the universe, you probably mean everything that is. But when astronomers say universe, what they mean is everything we can see. And I think this helps us rationalize concepts that we're going to get into, like the birth of the universe, because what we're talking about is actually the inception of everything that we can see. And that's a little bit more rational than the idea of things coming out of nothing, which is what the popular media often makes out of the birth of the universe. So at any rate, there's these, you can't really see it because it's black, dark, right? Cold things are very difficult to see. And actually, most of the story that we tell here concerns things that are hot and bright because that's what we can see, right? And science is inherently limited to the things we can see. We make stories out of evidence. We can't make stories that we can stand behind, at least, which are not represented by what is observable. Okay, so these white dwarfs are going to eventually radiate all of their heat away, and after billions and billions of years, the nuclei are not going to be moving around as fast, and it's not going to shine anymore. And these will be very difficult objects to detect, right? In fact, they'll look a lot like a cold moon of some sort, right? Mostly carbon, oxygen, neon, different products like that. So, you know, I think that there are interesting gems hidden in this process by itself, and we talked about a few of them last time. There's obviously extraordinary crises in planetary science in terms of explaining really dense bodies like the one that we're sitting on right now, which happens to be like the most dense object in the solar system. It's also very difficult for you to stitch little pebbles together and make a boulder, let alone make something as dense as the Earth, which is something like 5 times as dense as the sun on average. So, you know, I think there's room for growth in terms of understanding how these processes happen. And perhaps black dwarfs play into it if we find that the age of the universe is much greater than we had imagined. And then, you know, there's a couple of other processes too that can play into that. Now, I'm particularly intrigued by the possibility that stars could contribute to, that cold stars could contribute to planetary formation. There's an interesting study here that I wanted to just point your attention to. I may have mentioned it last time. It's called Vasco. And what Vasco did was it analyzed different frames from the sky over the course of like 50 years. And it found that a great number of stars actually had disappeared. Now, that could be for many reasons, right? They could be very slow period variable stars. They could be the stars that they thought were stars originally could just be artifacts. But there's still some percentage of these stars which they can't account for that seem to have gone missing, right? And so when we talk today about the fates of stars, all the fates that we're going to describe are quite explosive and incredible. Now, that could be the case because those are the things we can see very easily, right? Again, cold, dark things are very difficult to see. It seems like there are at least some portion of stars which go cold and dark, and we don't quite have a way to slot those into our understanding yet. So I'm very intrigued by this study. I actually am going to meet with this author not until April, unfortunately, so I won't get to report that back to you. But we'll do a podcast on it, and I think it'll be really interesting to talk to her about her ideas, and that, of course, paradigm shifts are very difficult in science. Most people are actually leaping to interpret such things in terms of, extraterrestrial civilizations and things like this, because in some sense they're easier to integrate than something like, well, we're going to have to revise this entire death story of stars because there might be another branch on this tree. But I don't know. We'll see. I'm really looking forward to speaking with this author, this investigator. All right. So let's continue with our story. Now, up to this point, we've been talking about low mass stars, but we got to talk about high mass stars at this point, really big things, right? So stars can get as big as 150 times the mass of our sun. And that presents a completely different paradigm. And it's thought that these stars, for the most part, die with a bang. And so in this case, the weight of all of the outer layers is sufficient to cram those carbon cores down, and they keep contracting until they can fuse the carbon into oxygen and neon and magnesium and heavier elements to a point, right? So this cycle of contraction and expansion of the shells continues again at this point, and it's going to continue much longer. And those carbon products can continue to be converted into even heavier stuff like silicon, sulfur, calcium, and argon, and we looked at a layered structure. And of course, this layered structure looks almost identical to the structure of the Earth, which is quite intriguing as well. So, and eventually these layers are also going to start to get blasted off. Now, the fusion of silicon into iron seems like the last point possible inside of a giant star. You can't really cram irons into one another. There's just not enough pressure available. And so we talked very briefly at the end of the last lecture about how we complete the story of element synthesis, how we get all of big, heavy stuff that we find on Earth all over the place. How does that happen? And so it takes essentially an explosion to make those things happen, because when you have these ridiculously energetic explosions, you actually have the opportunity for shock waves to cram these atoms into one another in a way that can lead to fusion of heavier elements. And that is where we head now. So something kind of interesting happens too when these high mass stars stop working, basically, when their fusion stops. So these, at some point, the other nucleons, right, become degenerate as well. So we talked about how at some points in the low mass stars, we get this degenerate electron material, right, which is essentially that the shells are no longer delineated from one another in these atoms. Now, the same thing starts to happen in these really high mass cores as well, except they've gone beyond that limit, and now they're nucleons, right? The structures of their nuclei start to break down. Now, you can think about nuclei as something like a knot of material, just like the shell is a sort of continuous surface of the atom. The nuclei are some sort of involution of that same material, and so the nuclei begin to lose their shape as well. And so this degenerate nuclear pressure actually holds back some content of the material from collapsing further and supplies a pressure outwards. And it turns out this pressure is actually way more intense than the degeneracy pressure of the electron, which we saw with the low mass stars, and it actually results in the star being blown apart. And that's essentially how we get a supernova. And so the halt of this compression, right, it's going to continue to be compressed to a point where it can no longer resist this nuclear degeneracy. And the sudden halt of that pressure actually is too much for the star, and it tends to send a shock wave throughout the outer layers, which blows them apart. Also, the compression itself results in the creation of a tremendous amount of neutrinos. Neutrinos are highly energetic, and they normally don't interact with ordinary matter. They normally are relayed right through. You can think about them as a kind of light almost. They're relayed right through most matter. But in the case of very compact, very high density degenerate nuclear matter, like what we're talking about here in the cores of these dying giant stars, you actually get a tremendous amount of interaction, and those really highly energetic neutrinos actually have all of the power necessary to blow these things apart. Now, this is an unimaginable amount of power, something like 10 to the 46th watts, which is greater than all the power put out by all the stars in over 1 billion galaxies, right? It's all in one moment, essentially. So this is the kind of situation that has the potential to make the energy transfers necessary in order to drive the fusion of these larger elements. This is the only thing that astrophysicists can think of which would be capable of synthesizing these heavy elements. And so this was the theory. And actually, when we go out and look at the spectra of these supernova remnants, we can start to see some of these heavier elements appearing. And we'll take a look at some of those here in just a second. So once they've blown off all their outer layers, there's still a small little core left, which is essentially this degenerate neutron material. We call the remnant a neutron star. And neutron stars are very strange objects, and they have some interesting behaviors that we'll get to here in a second. So let's look at a couple of pictures of these. So here we have 5 different explosions. These are from other galaxies. Now, yeah, it's worth pointing out that we haven't really had the opportunity to see any supernova in our own galaxy since we've had modern telescopes. There was a very bright one that appeared around the end of the first millennium AD. And this was well recorded by a number of different astronomers all over the globe. But we haven't actually seen one, so we're looking to other galaxies for these at the moment. Now, for historical reasons, the kind of explosion we're talking about here is called a type 2 supernova. We'll talk about type 1s in a moment. But the type 2s we can think of as the collapse of the explosion of these massive stars. So, it's worth also pointing out that these are so energetic that, like I said, the explosive power is so bright that it outshines the entire galaxy, right? These are very, very violent. You wouldn't want to be standing next to one when it happens, right? And in fact, they probably have important consequences for life on Earth. And there's a number of people who are speculating that different events in our geological past also can be tied back to supernova explosions that may have happened. All right. So this is kind of an interesting figure from your textbook. And I think that it lays out this idea that the appearance of almost all of the bodies that you see when you go out and stare at the sky from stars really have a strong mass dependence, right? So if you're small, you end up being a planet, right? There's still some sort of collapse process, and obviously the story of planets is wildly complex and incomplete, and we've been toying with some possibilities. If you are somewhat on the border of being able to become a star, maybe you stay a brown dwarf forever, until you're blown apart. And then as your mass increases, you're finding yourself moving into these more explosive patterns, right? So a lot of these phenotypes, that's a biological term, but a lot of the appearances of these bodies seem to stem down to how much material is crammed into a space at any given time. So, like I said, you can get some kind of interesting information about the contents and the material that's out there by looking at the spectra from these things. So we look at a few different, this is a supernova remnant. You can see this bubble-shaped gas and dust is expanding. And this is about 14 light years wide here. Let's see here. This was actually a supernova that we think was observed about 400 years ago by Kepler. And it seems like the remnant energy is mostly radiating in the X-ray band, and that we can gauge from the spectra that that expanding shell is very rich in iron, right? Which is quite fascinating. When we were talking about the molecular clouds that were responsible for the formation of stars and planets, we were mostly talking about these, tiny little, like all sorts of different gases, right? We think about a star being formed mostly of hydrogen, a bit of helium. But of course, there's a tremendous amount of heavy stuff out there too, right? These cores, when they're getting blown apart, when these iron chunks are getting cast out, we have some pretty seriously hefty building blocks from which we could consider planetary formation being important, right? And so I think that's important that the paradigm it wasn't very clearly laid out in your textbook, but we can't neglect the fact that there's a lot of heavy stuff left over from these supernova explosions as well. Some of them which might form the seeds of planets down the line, which is quite interesting. All right. And as we dig into the spectra of these supernova remnants a bit more, we can start to see all sorts of different material appearing. This is actually the remnant of this 1006 supernova that I was talking about before. And generally, by the way, these types, when I say type 1, type 2, these were categorized according to their spectra originally, but we're mostly going to focus on the cause of those supernova. Fortunately, like I said, the type 2 can be thought of as these massive stars collapsing. Type 1s, on the other hand, are a bit more complicated because they seem to happen when you have a regular white dwarf that would ordinarily just hang out there and cool down for the rest of its life. But it happens to be paired up with somebody who's feeding it mass, right? Another star. Something's feeding it matter, excuse me. And so it's growing on top of already being this degenerate white star. It's able to take up more material very quickly from its companion, and this leads to a different kind of explosion, which has slightly different spectral characteristics. We call those type 1 supernova. And I think this brings up an interesting point. So everything we've talked about, we've been trying to treat these stars like isolated events, but remember, almost every single star has a companion, right? We're very unique that we don't have a companion star, at least anymore we don't. We don't know what happened to it exactly, and there's all sorts of interesting hypotheses about that, and especially in terms of the origin of our particularly unique arrangement, right? Our solar system is very strange. I mentioned this at the beginning of class last time, but we have this very organized pattern with the little planets on the inside and the big planets on the outside. And for hundreds of years, all of our solar system formation paradigms revolved around trying to explain how these bodies formed in place the way that they were. However, last 20 years, we've been able to go out with this new Kepler program and look at all of these planetary systems that are forming, and mostly they're quite self-similar. They're mostly rocky planets that are all very similar in shape, and they're quite close to the interior. So there's definitely something on the move there, which is quite interesting in terms of how these bodies form in the first place, and perhaps the departure of a binary partner star could have something to do with why our solar system looks as strange as it does. And of course, that will be determined by your generation in the future. It's also quite intriguing just how beautiful and articulated these ring structures are that we see after following these supernova, right? I mean, they have these very beautiful blobs of heavy material already plopped out there in a ring, right? And of course, this is where we believe a lot of this heavy metal fusion is happening, right? Where these different layers, like you can think about it as shock waves in an explosion, are colliding with one another. There's already rings out there from the cast-off material from the red giant phase, and then this supernova explosion is forcing collisions with all of that new material that's crashing into the old. So there's certainly evidence of some sort of massively energetic collisions going on in these ring structures. And from the spectra here, we can pull out that there's all sorts of interesting stuff being formed. There's radioactive nickel, which is, of course, a huge component. Well, not radioactive. We have, actually, it stabilizes, right? But we have a lot of nickel in our own planet here. And the nickel spontaneously, this unstable nickel, it decays into cobalt, which we also find on Earth. The cobalt also decays into a more stable form of iron, and this emits gamma rays, which we can detect in the spectra. Now, the gamma rays are absorbed by the overlying gas, and we can see them being re-emitted in visible wavelengths. And this keeps the remains of the star visible to us in the visible wavelength. So let's keep cruising here. And of course, it dims over time, too. This is important, actually. So the particular way that it dims is actually quite important in terms of typing the supernova as well. And one of the things we'll talk about when we get more into the cosmology, when we talk about gauging distance to very far, far objects, right, beyond the scope of parallax measurements and so forth, has to do with examining the decay curves of these light signals. But we'll come back to that. All right, so neutron stars, they're quite interesting. One of the interesting features of these was sort of stumbled upon back in the 50s by a very curious and outside-the-box thinking scientist named Jocelyn Bell, who was at Cambridge, and she was studying distant radio sources, and she discovered one particular type of radio source that was somewhat inexplicable. It gave off pulses that were very focused of radio beams, right? Beams of radiation. And of course, just like everything in astrophysics and astronomy, when we see something we don't understand, people almost immediately claim that it's aliens, right? So they thought these were aliens, for sure. They might be, by the way. You know, it's a valid hypothesis to some extent, in that the pulses are very tightly clocked, right? So the thought was, well, maybe there's some sort of like navigational beacon from distant civilizations, right? And maybe they are, but very quickly, people began working on this problem, and they after actually beginning to call these things LGMs, which stands for Little Green Men, they came around to the idea that what these actually were was very fast-spinning neutron stars. So, of course, you know, just like any material, any glob of material, whether it's an atom or a star, it's gonna, if it has some sort of rotational quality to it, which almost everything does, it's going to, as it contracts, it's going to begin to spin even faster, right? And this is going to organize the way in which it radiates. And in the case of these objects, they radiate this particular radio wavelength out of their poles. And so this understanding, coupled to the observation of these LGM pulses, led to the theory that actually these aren't aliens, they're just very fast-spinning neutron stars, and they're acting sort of like a lighthouse, right, which has, you know, some focal radiation source that's spinning around, okay? So this is going to play significantly into our discussion of black holes as well, because when we start talking about how do we even find a black hole, what, you know, let alone what is a black hole, we'll deal with that. But how do we find one? Well, we're actually looking for interesting sources of radiation. And in the case of the black holes, this comes down to X-ray sources, but we'll play with that soon. Okay, so, I want to start thinking about systems that are more complex now than the simple isolated star systems we've been talking about, because most of the star systems actually involve secondary stars and interactions with secondary stars. So one thing that can happen in these star systems is that as the fresh hydrogen from the outer layers of a companion accumulates on the surface of one of these hot dwarfs, it heats it up and becomes even more degenerate. And the core can reach this temperature that causes fusion to begin again, and it happens in a very sudden, explosive way. We call this kind of explosion simply a nova, actually. Okay? So at some point, of course, this can accumulate so much material that it exceeds that Chandrasekhar limit, right, of 1.4 solar masses. That's going to lead into the back half of our story with the more exotic star deaths that we'll play with here in a moment. And actually, this collapse happens in something like less than a second. And all of this explosion happens, or all of this fusion happens at once, especially the fusion of carbon. And this leads to an extraordinarily violent explosion. And ultimately, we call these type 1s, okay? So let's compare the two, just to make sure that you guys have this straight, so that at least you can walk out into the world knowing the difference between type 1s and type 2s. All right, so type 2s originate, again, from the death of these massive stars. They're typically, we can distinguish the two spectroscopically because hydrogen lines seem to be absent from the white dwarf remnants that's going to go type 1, okay? Now, it's also possible that that a star, like say an ordinary star, could find itself sharing a star system with a neutron star. And that's going to make for really interesting interactions, right? Because in that case, it's going to be receiving infalling gas so fast that it's getting compressed and heated to these ridiculously high temperatures that you actually get this explosive burst of fusion. And we actually call these X-ray bursts. You can see these. So this is the kind of event that we would expect to lead to something like these spinning pulsing stars, right? These X-ray bursts. They're probably interacting with the star very nearby them and sucking up all of its material, these neutron stars. All right. So one more time, just to make sure before I leave this behind. This is somewhat important. Stars whose cores are less than 1.4 solar masses are going to run out of fuel, and they're going to end their lives as white dwarfs. And eventually the white dwarfs are going to cool, become black dwarfs. Stars whose masses are between 1.4 and 3 solar masses become neutron stars. And then when the core masses are greater than 3 solar masses, by the time they exhaust their fuel supplies, you're going to end up in a completely different pickle, which requires its own discussion, because that's where we start concerning ourselves with the limits of our understanding of gravitation, which leads us to the concept of black holes. And that is going to be a very fun and delicate discussion, which it looks like I'm going to have time to crack into here in just a moment. So, of course, like I mentioned to you briefly at the end of the last course, we also need to consider this alternative pathway with very, very borderline mass stars, right? These stars that we think they almost become stars. They're almost able to fuse hydrogen. Maybe they can fuse some deuterium, which is a heavy kind of hydrogen. We call them brown dwarfs. Now, there's borderlines, right? There's stars that sit on the border there, right? They're like, maybe they're one atom away from being able to fuse hydrogen, and so they become brown dwarfs. Maybe they lost that atom. I don't know. This is an interesting thing that I expect to develop in the next 10 or 20 years. There seems to be a path, right? A little sucker trail that leads away from our normal stellar evolution. Because as you can see, a normal star is going to progress through the stages we've been mostly fixated on. At some point, it's going to become a white dwarf star, right? What about these brown dwarfs, though? Well, they're eventually going to become quite cool, and over billions of years, they'll probably dissipate and turn down to something that looks much more like a cold planet. Who knows, after billions of years, maybe something that looks like a moon, actually. And so there's a very interesting story to emerge there between the bouncing between these two different paths, which I expect to play out in the future. Another way to think about it is to expand your HR diagram to actually include these cooler bodies. So if we were to just make the HR diagram a little bit bigger, you can see that the brown dwarfs actually sit on the main sequence quite nicely, except they're much cooler. And I think that's a fact which requires a great deal of imagination to puzzle into this sequence if we want to be completists about it. Now, of course, these are very, very, very difficult to see. Again, most of what we can see in the sky is on your left-hand side of the HR diagram. Anything that's cold and dark is going to be very difficult to make stories about at this point anyways. All right. Questions about all of this before we move into the final option? Yes, Travis.
You're saying that the structure, when the star structure resembles the structure of Earth, and you said it was close. How close is it?
Very, very close. Yeah, it's almost identical, actually, which is intriguing, at least. Yeah. So I guess I should mention this too. There was a Soviet scientist in the 70s named Oparin, who was actually quite a brilliant, I believe he was a geochemist, and he wrote a book called The Origin of Life. Of course, the Russians are kind of interesting, right? Especially the work they were doing during the Cold War years, because it was very separated from what was going on in the West. And much more so than anything that's happening on Earth right now, where obviously we share, despite what you'll hear in the news, we share a lot of scientific research with the East right now. That China publishes in many of the same journals as we do. There's a lot of dialogue. This wasn't the case during the 70s. And so the Soviets had a very different picture of how all this went down. And Oparin wrote a section in his book on the origin of life, suggesting that actually planets were on the continuum with stars. In fact, that there was an alternate path that didn't result in the explosion of stars, where these supermassive cores actually just cooled off and formed planets that looked essentially like our Earth. So the proposal from Oparin is that you are standing on a very dead, old, cold star, which is perhaps trillions of years old. They didn't buy the Big Bang thing. So yeah, so that's the idea, essentially. Which, I don't think you will find an astrophysicist alive in the West who would buy that right now, but I personally find it quite intriguing. I think it all hinges really on the cosmology that we embrace right now, which is a cosmology which says that the universe is 14 billion years old. That's not enough time for this process that Oparin has suggested to occur. But I do think that it's interesting, again, this is why I want you to really understand what people mean when they say universe in an astrophysical context. They really just mean how old is the stuff we can see, okay? And that's a very different matter than how old is everything that's in existence, which is a very different question. So I don't know. This is, it's not really my job to pass judgment on that for you, but I do think that it's an interesting coincidence to point out. And there are some serious, like I keep coming back to, there are some serious struggles in producing a planet that looks like this. It's not so easy as just accreting matter, which is the typical textbook story. There's actually some extraordinary problems with that, particularly this idea of crossing this meter-sized barrier and cramming together pebbles and to make a boulder. It's just not possible, right? And people have played with different ways of making it possible, right? There's ways that you can imagine slowing down material with dust and gas and these different braking mechanisms. And so those tend to be what people favor right now. But they're, it's an issue. And there's other issues. The angular momentum issue is quite disturbing too, right? Jupiter contains most of the angular momentum in our solar system, which is very bizarre, right? If our formation model for how all of this stuff got here has to do with the accretion of material because there's this spinning disk, and the sun is essentially at the center of it because it's spinning the fastest, well, why aren't the suns spinning the fastest, right? This is a tricky thing to explain, right? And so in some sense, I can sympathize with Aparin because it's a lot easier if you start with a planet and then you just drag it into your star formation process and then, okay, well, these things were out there. We couldn't see them because they're cold. And so naturally, we just scoop them up. And so the planetary systems are something like thrift stores, right? They're just picking up pieces from past lives, right? It's a very small but subtle difference. In fact, obviously, your textbook will tell you that all of the building blocks for your planet come from dead stars. And so what Aparin has proposed he's very dead by now, but what he was proposing was not too super different from that. He's also saying, yes, the building blocks for planets come from dead stars. They're just a lot more well-formed than we generally think of them. So yeah, keep an eye on that. That's something. I wonder where this will all lead into the future. There's no science that I'm aware of that is changing as fast as planetary science. The Kepler probe, the creation of entire departments devoted towards exoplanets and exobiology. This is just a massively expanding field of science. And so we're learning so much all the time. It wouldn't surprise me if the paradigms are 180 degrees different 10, 20 years from now, which is really exciting. You guys can, 10, 20 years from now, talk about how crazy your textbook was when you were kids. All right. So let's, I want to set the stage today for the concept of black holes. And I'm not going to actually do black holes today because what I want to really, really do next time is take the time with this luxury of depth to explore the evidence that's there and explore the interpretations that are given. And in order to do that, we have to understand how we even came up, how astronomers even came to the conclusion that such an extraordinary and unintuitive object could exist. So I want to be very curious about this process as I explain it to you. I want to present to you what your textbooks explains, and then, as always in this class, I want to take the position of the skeptic, which I think is the proper scientific thing to do, and examine issues with that theory and what might change in the future, because I think that's what really matters to you guys as the younger generation, because your job is not just to sit there. If any of you become scientists, I expect maybe one of you will, and your job as a scientist is not just to sit there and defend old theories. Your job is to think of better ways of explaining nature. And so, Richard Feynman, who is one of the most well-respected physicists of the 20th century, famously said that religion is a culture of faith, but science is a culture of doubt. And so I think it's very important that we approach things that go against our intuition very cautiously, and we actually pay attention to that, and we really consider that perhaps we don't have all of the answers in any case. So the basic principle here that we're going to crack open right now is that most of these stars that we've talked about end their lives as white dwarfs or neutron stars. Now, when an extremely massive star collapses at the end of its life, there's not even the degeneracy pressure of the neutrons can support the core against its own weight. This is the thought. And so the idea is that if the remaining material in the star's core is something like 3 times the mass of the sun, the extant theories of gravitation, which we'll talk about with some luxury here in a moment, predict that no force can stop it from collapsing forever. Now, I actually think your textbook does a really good job of being somewhat tacitly skeptical of this concept in the first place. It's very important to take note of the important clause here that our theories predict that no force can stop it from collapsing. Now, what theory are they talking about? Well, they're talking about our theory of gravitation, which is an interesting use of the word theory, because this word theory is actually quite abused along with the word hypothesis in science, and most people don't really, they don't use it in a consistent way from presentation to presentation. So let's say you are engineering a rocket propulsion system. Well, in that case, you might have what you would say a theory, which is a mathematical representation of the components of your rocket system, which allows you to tweak different variables in it, say the amount of fuel or the temperature of the fuel, something like this, right? So a theory in engineering is, generally speaking, a mathematical description of the phenomena which has been parameterized in a way that allows you to manipulate it. Now, science is a bit weirder, right? And in science, oftentimes, I would say 100% of the time, we're explaining something that we've already seen. So we're explaining something in the past in science, always. Now, sometimes that can be the very deep past if we're trying to explain something geological or astrophysical. Sometimes we're just trying to explain something we saw in a test tube 5 minutes ago, okay? So in science, as opposed to in engineering, theories generally have to propose some explanation for an observed phenomenon, okay? The interesting thing about what the textbook and what we're generally calling the theory of relativity is that it's actually a mathematical description of what's happening, right? It has parameterized the variables, in this case, mass, right? The pull of atoms upon one another, and space, the location of these atoms with respect to one another. And it's generated, Einstein and his collaborators have generated a very precise way of describing reality in terms of these parameters, okay? Now, does that mean that we have a mechanistic explanation for what's actually causing gravity? In other words, what the atoms are doing to one another in order to produce this pull? Absolutely not, okay? So this is the wonderful, I don't want to call it a blind spot because I think it's actually a beautiful place for imagination, because we don't totally understand how atoms produce gravity. You'll hear people, one of the biggest topics at the edge of fundamental physics right now is the search for quantum gravity. And you're like, what do they mean by that? Well, they're trying to understand how atoms actually enact this process of gravitation upon one another. Relativity doesn't do that. In fact, I used this example of the magic show at some point at the beginning of this class. And in case any of you weren't there, I'll just briefly restate it. But with relativity, the idea is something like this. If you are looking at a magic show on stage and there's a woman getting sawed in half by a magician, what relativity would do is it's going to tell you what that sawing behavior looks like from every angle available, right? And it's going to do it very precisely, actually, with high predictable accuracy. But would you ever find out that the woman moved her legs up inside of the box and didn't get cut in half? Absolutely not. You would never realize that. Okay, so this is the difference between an explanation and a description. Now, mathematics is fundamentally a descriptive notation. Mathematics never, ever explains anything, ever, no matter what anybody tells you. Mathematics needs some language, like the one that I'm using right now, in order to articulate the concepts to explain the mathematics to you. So, unfortunately, for the pickle we find ourselves in with this black hole phenomena, we are viewing a model, a mathematical model of reality, which we call general relativity, which is highly accurate. However, it doesn't give us much insight into the actual material mechanistic explanation of what is causing that gravitation, okay? Now that I've taken a shot at relativity a little bit, I do want to laud some of its benefits, right? It is actually an extraordinary revelation here, and I think it can give us some insight into what gravity actually is. And that comes in the form of a thought experiment, which Einstein stitched together. Now, Einstein got this idea from a very, I think a very great thinker named Ernst Mach. And certain pieces of physics still bear his name, right? We hear it in the speed barriers of sound, right? Mach 1, Mach 2. Okay, so Ernst Mach was thinking about this a bit. And before we talk about Einstein's conception of it, Ernst Mach had this idea. He was thinking about inertia, right? And he was thinking about gravity. And he was thinking, why is it that, even if you go out into space, obviously they couldn't go out into space then, but they had the revelation that still, if you had a body in space, that it would essentially stay put, or at least it will just keep going on the trajectory that it's set on until something interferes with it. And you take this back to Earth and you think about it. Why is it on Earth that if, I stand here and I spin around, why do my arms fly out to the sides, right? It's a very interesting question, actually. And so Mach thought about this, and he thought, well, the only reason this could happen was if my arms were attached to everything else around them, including all the stuff above me in the stars, right? So Mach had this conception that inertia, the tendency for bodies to remain where they are, and the difficulty actually of moving them, had to do with the interconnection of material in the cosmos in general. So things appeared to be connected to the things they were next to, no matter how far away they happened to be. And of course, the connectivity seemed to scale with distance in this inverse square relationship that Newton famously pointed out. Now, Einstein took this idea very seriously, and I think this is one of the most brilliant things that he did. By the way, before I even get into that, Einstein was very famous before he came up with any of these, before he was famous for these ideas. So Einstein actually did a great amount of work when he was a grad student on molecular motion. And he eventually did work showing how the absorption of photons can lead to the generation of electricity, and that's what he actually won the Nobel Prize for. So most people think he got the Nobel Prize for this stuff with relativity. That is not the case. He actually got the Nobel Prize for the photoelectric effect. And I think that actually says something really important about paradigm shifts in science. If you can do something that is fundamentally practical, like the photoelectric effect, which of course led to all sorts of wonderful inventions, if you can establish yourself in that way, maybe you can come up with more theoretical ideas that people are more willing to entertain. So Einstein started thinking about this Mach's principle thing a bit. And of course, he realized that we have two giant laws which we inherited from Newton. The one on the left is essentially an inertial law, right? It tells us that you have to essentially work to move something, right? If you want to accelerate a body that has a mass m, you have to supply some force to it, right? So this quantifies inertia, essentially, the tendency for bodies to stay at rest if they're at rest. Now, he also realized that the force of gravity can be expressed thusly, which we've talked about earlier. And then he started thinking about this a bit more, and he realized that, devoid of context, that these two processes would actually feel and seem and appear to be similar, actually. So as you can see this, if you're isolated in an elevator and you're experiencing gravity, as you fall, you actually feel lighter, like you're weightless. But in reality, you're actually just accelerating downwards, right? Likewise, if the elevator suddenly moves upward, in the moment where it's accelerating, you're going to feel additional weight, right? This is actually I think this is quite remarkable because, while Mach realized that that inertia seemed to have something to do with the connectivity of the bodies around you, Einstein really stitched it together and realized that actually, in fact, inertia and gravity were completely equivalent. And, he processed this idea mathematically to an extreme, which is actually how he developed the theory of relativity. And I'm not going to torture you with the math behind that. Perhaps if you take a more advanced astrophysics course, you'll have the opportunity to see how you can derive general relativity. But it's actually not too bad if you have a little bit of basic calculus in your pocket. But we don't have to do that today.
I think that it should suffice us to understand that by putting these two equations equivalent to one another, a number of interesting features fall out. And once he processed that mathematically, it turned out that he produced a relationship between mass and distance, generalizing it into 3 dimensions, which we call space, which was extraordinarily accurate. It actually, one of the first successes was that there had been this troubling discrepancy between the orbit of Mercury as predicted by Newton's simplified gravitational law and the observations. Now, it was just a tiny little discrepancy, but it was there. And so one of the first successes of Einstein's formulation was that it was actually able to recapitulate this deviation from Newton's laws with respect to Mercury's orbit. And I think this really won over a lot of people very quickly. Now, another thing that's interesting is that Einstein really embraced the idea that time, in an astronomical sense, was very much able to be transposed into distance, right? If you have a constant travel time. Now, this gets us more into special relativity, but one of the postulates of special relativity, which is not the gravitational side of things, this has more to do with light. One of the fundamental assumptions of that theory is that the speed of light is the same in all reference frames, which is a very, very peculiar quality, which we don't really have time to take apart right now. But at any rate, Einstein surmised that essentially because of this property, that space, the dimensions and the distances, could be easily determined from understanding travel time of light. And so he packed these into one concept, which we call space-time, right? And so the way that general relativity is generally, the way that general relativity is broadly understood is in terms of the distortion of this metric, which is called space-time. And one of the consequences of that is gravitation. And another consequence of that, which is a bit more perhaps troubling, but also plays into our concept of black holes, which we're working towards, is that if space-time is itself distorted, if the whole basis for all motions is distorted, then light also should be distorted by gravitation. And so this was quite a claim, right? Because light is generally considered to be massless and so forth, right? So we wouldn't expect it generally to be distorted by gravitation. However, we'll see there was actually an interesting test that was performed, which seemed very quickly to reinforce the idea that this was happening. There's other tests too that have been brought out, which I want to point out to you as well. And your textbook mentions at least one of these. So, it's often stated that your GPS wouldn't work without using relativistic corrections for the time dilation as a result of the GPS, coming into contact with the gravitational forces of the Earth and stuff. And I think this is true. Now, does it mean that time itself is being distorted, or does it mean something else? Well, I think it's important to ask yourself, what does time mean in these equations? Well, it turns out time means what the clocks are doing. Okay, so the clocks on these satellites are changing, right? Now, the first test of this was kind of interesting. There's actually a broken communications satellite. It was supposed to be stationed in this nice circular orbit around the Earth, but one of its thrusters broke when it was being positioned, and it ended up in this highly elliptical orbit around the Earth. And they noticed that as it came closer to the Earth, that the clocks slowed down a little bit. And as as it moved away, the clocks sped up. Okay, so everybody thought, okay, this is great. This proves that time itself is slowing down in the presence of gravitation. But I think this isn't quite the right way of looking at things, okay? Because, clocks are material objects. They are absolutely subject to gravitation. This makes sense. let me ask you this. If I take a, if I take a, let's say, a simple geared clock, right? Or how about a pendulum clock, right? Which works based on the gravitational pressure of the Earth. And I take that up to the top of a mountain. There's going to be less gravitational pressure on the pendulum, and it's going to swing faster. Now let's take a really extreme example of that. What if I take an hourglass? It's a great clock, and I take it out into space. What happens? Time stops. Yes, time stops according to this system. What's up? Unless you shake it. So I think it's very, very, I think that the popular media would love you to believe that there's something spooky going on here, but I don't think that it's quite that simple. I think that it's totally reasonable to believe that when you have a bunch of atoms crammed into one space, that the pressures they're going to exert on your clocks are going to be very different. Now, the clocks that we use today for very precise measurements are atomic clocks. And these atomic clocks work essentially by looking at how many times these atoms are vibrating per second, and they vibrate very, 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 very fast. And then they take these atoms out into away from the Earth a bit, and they vibrate slower, right? And again, I don't think that the conclusion here should be that time itself is slowed. I think you've just relieved the pressure on those clocks. The atomic pressure on these clocks has been relieved. So there is two ways to look at all of this relativity business, right? There's one way where you say, wow, like the fundamental fabric of reality, time and space, is being distorted. And another way where you say, time and space are metrics that describe reality, and reality is behaving differently because the actual materials, the atoms, are under different pressures in different environments, depending on how many of them there are in one place, which I personally think is a lot more reasonable. Now, the light thing is quite interesting because the whole back half of our discussion on black holes depends on the idea that light can be affected by gravity, which is more or less universally accepted at this point. And let's think about why that is, okay? So Einstein wrote all of his papers in German, and this was back during a period of history where people who didn't speak German on the continent and in Europe and in the UK, they weren't very interested in speaking German either, right? This was when the wars were going on, all right? They didn't like the Germans very much. So part of me thinks that if Einstein had just kept writing in German, maybe you would never have heard about him, actually. But a British astronomer named Arthur Eddington, who's come up very, very many times, whom I've compared to the Neil deGrasse Tyson of his day, he actually read this paper in German and was quite taken back by it. And Eddington translated it into English, and he actually wrote a blurb for the very popular, actually the most popular journal on Earth right now for science, which is called Nature magazine. He wrote a piece highlighting it, and he actually proposed a test of Einstein's relativistic formulation of gravity. He said, well, if light is actually being bent by stars or by heavy objects, perhaps we can see this if we go and look during an eclipse. So in 1919, he organized two different expeditions. He went to this little island off the coast of West Africa, and another team went to Sobral, which is in northern Brazil. And they took some photographs of stars in their position during the eclipse when the sun was actually right next to them. And he obviously compared them to photographic plates of them in the clear night. And what he found was that the deviations during the eclipse, when the path of light from the star was being potentially affected by the sun, that those deviations were reasonably within accord with general relativity. I think they were within 20% of the predictions of general relativity, which, by the way, probably wouldn't get you very far today if you had 20% error bars on your measurements. But at any rate, he popularized it, and I think basically from that moment, this idea that light was being bent by stars was taken as gospel from that point. Now, we've actually been able to confirm these measurements pretty tightly up to this point since then. And so it does seem that light is being affected by these stars. Now, so the question is, why is that happening, right? because, again, relativity just tells us that it is happening and that it's happening in this particularly quantifiable way. I spent a lot of time thinking about why this is happening materialistically in terms of the atoms, and I actually only came across one fairly legitimate scientist who had a decent theory about this. His name is Edward Dowdy. He actually just passed away, sadly, but he was a laser scientist at NASA, and Dowdy published this one paper, and he basically said that the he actually had 3 points, which I think are very salient, and I think that I think I'm going to kind of leave you with this little story. Again, the job of this scientist is to be skeptical, not to just buy into everything just because it seems cool. And Dowdy said, one, there's something very interesting here. It seems like this light bending phenomena only occurs in the limb of the sun. That is, only in this plasma boundary of the sun. In other words, if gravity itself is bending light, then there should be distortions of the other stars at several solar radii, at least 2 solar radii away from the sun, right? So way out here, we should still see some lensing going on, but we see none. In fact, all of the lensing only occurs within the corona, which is quite fascinating. Dowdy also points out that some of the other lensing events that we see, maybe you've seen some popular headlines with these Einstein rings around galaxies, right? He points out that it's strange that there's countless number of candidates for these gravitational lensings, but we actually only see a couple of them, which is quite strange. In fact, he states something like, well, if this light is actually being bent by large masses, then pretty much every star you look up and see in the sky should have a little ring around it, essentially, because there's so much stars stacked on other stars behind it, which I think is another interesting point. He also makes the point that the supposed black hole at the center of our own galaxy, Sagittarius A, does not interfere with light whatsoever, any light paths coming from that region. So there's a number of contradictory elements, and what Dowdy ends up proposing at the end of this paper is another mathematically equivalent formulation of the lensing that we observe in the plasma limb of the sun, which has to do with the exotic state of the superheated material that's in that plasma, which actually acts just like a lens itself. So I don't know if he's right or not, but it's certainly an interesting proposal that is congruent with the same mathematical presentation. And we don't, like I said, have an actual explanation. We have only this very, very precise description, which we call general relativity. And everything that follows after this point, where we're going to talk about these end-stage stars, you've got to understand that those end-stage stars are a prediction of general relativity. Now, all mathematical models, right? I'm actually in the process of publishing one myself right now that has to do with the way that water behaves under certain confinement conditions. You need to put a boundary condition on any mathematical model. As in, at some point, your theory, your mathematical model, it's going to fit some data points, but not all of them. And if it's a good model, it can fit a lot of them in one region, but you draw the lines at some point. You say, my model only works up to this point, right? And so I think a lot of the confusion that we're facing right now in terms of the inability to unify the quantum world with the world of general relativity has to do with not ascribing boundary conditions to either one of those models, right? And in this case, when we extend Einstein's laws out to very, very far extremes, we end up with some rather unreal conclusions, which I guess is where we will pick up on Thursday, and we will go through the evidence and talk about the black hole. All right, have a good couple of days. I'll see you Thursday.